How many of you feel completely comfortable doing a sum of forces on each axis and on doing a net force using 2 axes? 0 to 5. 0, I have no idea what a force is. 5, I could take a test right now. Okay, lots of 3s, 4s. Okay, lots of 3s and 4s. That's good. Here's what I have seen in years past. People freak out a little bit on 4A. Oh my God, this is so hard. Ah! And then we go to 4B, and they go, wow, 4A was really easy. 4B just adds a little bit, but I think it actually contextualizes this stuff. What we haven't talked about yet, we've just been talking about net force. What did we say at the very beginning forces did? They move things. They move things. What was the t-shirt I saw? Of course the world isn't flat. If it was, cats would have pushed everything off the edge by now. They move things. Because you've all seen cats do that. Tap, 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 tap. Okay, so now what we're going to move into is actually moving things with forces. And we're going to talk about inertia a little bit. So my favorite example is always a semi-truck load full of cinder blocks versus a Honda Civic full of cotton balls. Hit both of them with the same force. One of them is going to accelerate at a higher rate. One of them is going to move farther. You can take a lead brick and a ping pong ball. Things that have larger mass, when hit with equal force, have smaller accelerations. The bigger you are, the more force it takes to accelerate you. That's kind of, it's something you understand intuitively. If you've pulled a sibling, cousin, neighbor kid up the hill, there's always that one like skinny, scrawny little kid, and then there's like the really good, sturdy chunker kid. You want to be pulling the little skinny, scrawny kid. You don't want to pull the really solid kid. Because it takes more force to get more mass moving. This is at the heart of that. F equals ma. And I have my shirt on. May the mass times acceleration be with you. I have no fewer than 3 t-shirts with F equals ma jokes on them because, you know, that's what science teachers do. This is going to center all of our calculations from here on out. We've been doing net force. You know how to find net force. Well, now what we're saying is that the net force is equal to the mass of the object times the acceleration the object is undergoing. That inertia is the tendency of objects to maintain their state of motion. The tendency of objects to not accelerate or to continue their velocity or to continue their state of stillness. And it's proportional to mass. So heavier, things that have more mass have more inertia. Things that have less mass have lower inertia. We do see this in seatbelt systems and trailer. Has anybody here ever driven a trailer? A truck with a trailer attached to it? Okay. I was probably 23, 24, and I got hired by the Division of Wildlife on a fish survey crew. Whee! And it was a couple of old guys and me. And they said, can you drive a truck? And I said, sure. You ever driven a trailer? Little ones. Okay, we're going to go to sleep. And I got handed the giant Ford F, I don't know, 750 or something with the 23-foot boat trailer with the boat on it. And they went to sleep. She'll be fine. Okay, I was fine. Spoiler alert. But one of the things that I remember before my boss went to sleep, he said, now watch it, the trailer's a little pushy. Okay. What he meant was that you get the truck moving, you get the trailer moving. You put the brakes on the truck, guess what the trailer wants to do? Keep moving. So you have to increase your stopping distance. You have to brake sooner than you would think so. than you would think you would have to, because the mass of the trailer is pushing you. Well, what they've done mechanically is trailer brakes largely work on the following. So this is the world's worst drawing ever of a trailer brake system. A lot of trailer brakes on larger trailers actually have a mechanism in here that floats. So as the truck stops and the trailer keeps moving forward, it ends up exerting a force back inside that hitch. And that applies a brake on the trailer. That's an inertial braking system. You're using the inertia of the trailer to brake it. And I think it does link up mechanically to something else. I'm not an expert in trailer brake systems, but that's sort of the, I don't know what, the 30,000-foot overview. You can look into them. Seatbelts do some similar stuff. Your seatbelt locks up when the car is braking because of an inertial braking system inside the seatbelt mechanism. So we've talked about, oh, that's not spelled correctly. Well, forget that. Oh, well. We've talked about equilibrium we haven't talked about equilibrium in here, have we? We talked about it in chemistry. We haven't talked about it in here. So equilibrium is the state of things being, I know this is really shocking, equal. And when we say that a physical system is at equilibrium, we're saying that the net forces on it are zero. Now, there can be two conditions under which net forces are zero. Remember, net force, not force. If something is sitting still, does it have any acceleration? No. If it doesn't have any acceleration, net force equals zero. It's at equilibrium. If it is at constant velocity, its velocity is not changing, does it have any acceleration? No. If it doesn't have any acceleration, its net force is zero. It's at equilibrium. This is going to become really critical to problem solving. How do we figure out if it's at equilibrium? I'm glad you asked. Sum of forces! Oh, sum of forces, how we love thee. Every single time we look at an object, we want to start with sum of forces with these kinds of problems. And if the sum of forces on both axes is zero, then that object is at equilibrium. We can also look at an object and say, is it accelerating in any direction on any axis? No, it's at equilibrium. Those are mostly the kind of problems we've been doing up to now. We've mostly been doing problems where, well, the sum of forces on the x-axis is zero, sum of forces on the y-axis is zero. And that gives us the hook into the problem. So whenever we have sum of forces equals zero, it's at equilibrium. We're now going to start doing problems where objects are not at equilibrium, where they are experiencing acceleration. Objects at equilibrium have zero net force. They have zero acceleration. We can also know that when an object's accelerating, we said inertia is proportional to mass and acceleration. That's where we get F equals ma. So now what we can do is say, well, the net force is equal to the mass times the net acceleration of the object. Great. Do you know how to find net force? Of course you do. You start with your sum of forces on each axis. M is the mass of the object. This is the net acceleration being experienced. And that is the sum of all forces on the object. So now what we can do is look at any object and figure out what effect a given force will have on it. So we're going to do sample problem 4B together, and then we'll talk about a couple other little bits and pieces. Okay. Roberto and Laura studying across from one another at a wide table. Laura slides a 2.2 kilogram book towards Robert. Net external force on the book is 2.6 newtons to the right. What's the book's acceleration? Well, this is easy. This is so easy. This is ridiculously easy. net force equals mass times acceleration. We're given the net force. We want the acceleration. So I should get the sum out of there. It's kind of redundant when you're saying F net. F net divided by mass equals acceleration. Aw, that's so easy. F net was 2.6 newtons, right? Mass was 2.2 kilograms. Our acceleration, 1.181818. What are my units?
Meters per second squared.
How do I know that? Newtons divided by, what is a newton? A newton, 1 newton equals 1 kilogram meter per second squared. Because it's the amount of force required to accelerate a 1 kilogram object at 1 meter per second squared. Okay, so with sig figs, what do I get out of this? I get 1.2 meters per second squared is the acceleration of the object. That's ridiculously easy. If they were all like that, life would be a dream. Let's do, you like the dream? You want to live the dream? Of course, I can't let it be that easy. It's not that easy. Let's do one that's not that easy. So this is just one kind of off the top of my head. You've done lots of things now with force of tension. We've suspended, mastiffs and zebras and gorillas and who knows what else. Boxes and bags and plates of cookies. Well, what if we've just suspended them. We've just had them hanging there so that the sum of forces is equal to 0. Well, now what if we accelerate them? That would complicate things, wouldn't it? Yay! Well, we've got a 15 kilogram mass being accelerated upward at 3.5 meters per second squared. What's the net force on this object? So you want to take a wild, crazy guess what we start with? All together now. Sum of forces! Of course we start with the sum of forces. So sum of forces on the x equals 0, and we don't have any listed forces on the x, so we can just set that aside. There are no forces on the x as far as we know. We're not told there are. Sum of forces on the y. Well, it's not 0. That has changed. But something is still true that has been true all along. The sum of forces on the y is equal to what? Forces up minus forces down. Okay. Well, my shirt would tell you, and the equation that we just got would tell you, that the net force is also equal to mass times acceleration. And since this is true, the net force is really just the sum of forces on the y-axis. There are no forces on the x. Woo, sorry. So sum of forces on the y equals ma. Do you see what's coming? No? I think you do. Well, that means we have two things, and you know how we love to set things equal to one another. So mass times acceleration is equal to all the forces up minus all the forces down. Now, in the past, when these things were just suspended, there was 0 acceleration, therefore ma equaled 0. So we just didn't talk about it. But now we're going to talk about it explicitly. So ma equals, well, what force up do we have? Force of tension. What force down do we have? Force of gravity. And actually, I should have made this, what is the force of tension on this object? That's what we're going to look for, is the force of tension. Net force is too easy. Can't make anything easy. So intuitively, let me ask you this. Just thinking about this sort of rationally, and I don't want you to say this out loud. I want you to just kind of jot it down or make a note of it in your own head. Do you feel intuitively like the force of tension is going to be more or less than the force of gravity? Don't say it out loud. Okay. Well, to solve for force of tension, we got to do some algebra. Well, MA, we're going to move the force of gravity across the equal sign, plus FG equals FT. Well, what's force of gravity in reality? That's MA plus mass times gravity equals FT. This is where, if you had a problem where you needed to solve for mass, it would be very easy to factor out mass here. You can factor out mass here if you want. You don't have to. I'm going to do it just because it's sort of habitual at this point. So now, do we have everything we need to solve this? Sure. 15 kilograms times 3.5 meters per second squared plus 9.81 meters per second squared will give us the force of tension in that cable. Okay, so I've got a raw answer of 199.65 newtons. We have, what, 2 sig figs because of how poorly the problem was written. So 2.0 times 10 to the second newtons is the force of tension in the cable. How does that compare to the force of gravity on this object? How would we figure that out? 15 times 9.81. So F of G on this object is 15 times 9.81, 147.15 newtons, or 150 newtons. So it's about, what, a third again as much? Does that make sense? The thing that people always do with these kind of problems the first time they get them is they go, oh, well, mass times acceleration, 15 times 3.5. But what you're forgetting is that just to hold it there, the force of tension has to be equal to gravity. So to do anything that accelerates it upward, you're going to have to overcome the force of gravity first. Then you have that added force on it. Questions? You know what that is? It's actually a swimming pool, and that's somebody's keys in it. Actually, it wasn't keys. It was a stainless steel screw, but it was also winter, and nobody really wanted to go in the pool. And I was one of the people involved in this scenario. I think he might have been my boyfriend then. I don't think he was my husband yet. But anyway, same guy. He says to the physics teacher, there's no way we can get that out. Somebody's going to have to go in the pool. I said, just watch. So we had a rare earth magnet, and they're really powerful little magnets, and I had a piece of string. He said, yeah, but it's not strong enough. The magnet's not strong enough to hold that thing under the water, to move it upwards. I mean, I can get it, but I can't get it. It keeps falling off. I said, well, your problem is what? So how did I use what we just did to successfully get the stainless steel screw out of the pool in the dead of winter and not have to get wet? You tell me. I'm pausing this. Okay, so you guys are smart, clever little critters, and you know that the big key here is keeping acceleration as close to zero as possible. Our fishing trip was successful. People successfully pulled the pair of pliers up over the balcony. All the 4B book problems are assigned, and the 4B worksheet will start with the odds, and we will probably have to do the evens as well because people get all hung up on these. I'll get the worksheets for you. Blizzard bag tomorrow. If we are not here, which is a strong likelihood, finish the 4B problems. I have to give you like some stupid little thing so I can check a box that you did it. So you'll have another little like reading or a short little, video about a physics topic. But the real blizzard bag is keep moving on 4B.